Hello friends, welcome back to my YouTube channel. This would be ninth part of my discussion on leaching. I will continue my discussion on stage-wise leaching, and in this video, I will solve a numerical that is based on multistage counter current leaching. The theoretical aspects of multistage counter current leaching I have discussed in part number 8. I am giving link to the entire playlist of my lectures on leaching. In part number 8, that is in my previous video on leaching, I had discussed the theoretical aspects of multistage counter current leaching. Now we are going to use those concepts, the concepts that were discussed in part number 8. We are going to use those concepts to solve a numerical. So at the end of this discussion, you'll be able to calculate, you'll be able to learn many things. You'll be able to calculate a percentage of solute that is leached out, how to calculate percentage of solute leached out, then how to find out equilibrium stages. Plus, you'll also learn many other things that are very important for solving a numerical, any numerical that is based on multistage counter current leaching. So let us start the discussion. To begin with, we will look at the numerical statement. 360 kg per hour of halibut liver is to be leached out in a counter current cascade to recover oil. The solvent used is ether, which has been recovered from a previous operation. Therefore, ether contains 2% oil in it and it is admitted into the operation at a rate of 250 kg per hour. The fresh liver contains 25% oil and it is to be extracted to a composition of 2% on a solvent-free basis. What percentage of the oil in the entering liver is leached and how many equilibrium stages are required in the operation? So you have the feed is liver of the halibut fish. The liver contains oil in it and the task is to recover that oil by using leaching, by using multistage counter current leaching. The feed, which is halibut liver, it is admitted at a rate of 360 kg per hour. The solvent used in this case is ether, but it is not pure solvent, it is a recovered solvent. That's why it is containing 2% of oil in it. And it is admitted into the operation at a rate of 250 kg per hour. The fresh liver, that is the feed to the operation, it contains 25% oil and it is to be extracted to a composition of 2% on a solvent-free basis. That means the oil content in the liver is to be reduced from 25% to 2%. That is the task. And for this task, what is the percentage of oil that enters the operation? What percentage of oil is leached out when you try to reduce the oil content from 25% to 2%? First thing is, we are supposed to find out percentage of oil that is leached out. That is, out of the oil in the feed, how much oil is leached out? This is the first question. And the second question is, we have to find out the number of equilibrium stages that are required in the operation. Okay, along with all this information, we are also provided with the equilibrium data. And in that, we have different values of kg oil per kg solution in exhausted liver and kg solution per kg exhausted liver. And you have values for these two quantities and these values are in equilibrium with each other. So you have these values and we will use these values in our calculation. Okay, so first of all, let us know what is given to us and what are we supposed to find. So the process involved in this case is leaching of oil from halibut liver using ether as a solvent. So you have halibut liver, there is oil in it, and the task is to leach out that oil by using ether as a solvent in a multi-stage counter-current leaching operation. So leaching of oil from halibut liver using ether as a solvent in a multi-stage counter-current leaching operation. That is the process. Now let us represent it with a simple schematic. So let this rectangular block represent the cascade, multi-stage counter-current cascade, in which multi-stage counter-current leaching is carried out. Feed to the operation is halibut liver, and it is admitted at a rate of 360 kg per hour. This is given to us. It is containing 25 weight% oil, which is the solute in this case. 25 weight% oil, and remaining 75 weight% could be insoluble solids, that is B as per our notation. Then it is contacted in a counter current manner with a solvent, which is a recovered solvent, and it is admitted at a rate of 250 kg per hour. Since it is a recovered solvent, it is containing some oil in it, some C in it. It is containing 2 weight% of oil in it, and the remaining 98 weight% would be ether. So this will produce the underflow. In this case, it is exhausted liver or leach solid. Underflow is containing 2% oil, that is 2%, 2 weight% oil, 2 weight% C on a solvent free basis. That is kg per hour of C divided by kg per hour of B plus kg per hour of C in the exhausted liver is 0.02. That is the weight percentage of C on solvent free basis is 2%. And if you convert this percentage to fraction by dividing it with 100, it would be 0.02. And then you get the overflow, which is simply solution of oil in the ether, and no other information is provided regarding the overflow. What are we supposed to find out? We will find out percentage of oil left and then percentage of oil left unextracted, because that will help us to get percentage of oil that is recovered, percentage of oil that is leached out, and then we can report that value. We are supposed to report percentage of oil leached, and for that we need to find out percentage of oil that is left in the exhausted liquid. So once we know that, we will be able to report percentage of oil that is leached. This is one question, one part of the question. The second part is we have to find out number of equilibrium stages that are required to achieve this separation. So with this given information, we need to find out percentage of oil that is leached out, and we also have to find out number of equilibrium stages. So I hope the numerical is clear to you, or what is given to us, it is clear to you, and what are we supposed to find out, it is also clear to you. So let us move ahead. Okay, the other information, let me just tell you one more thing. If the exhausted liver is containing 2% oil in it, rest 98% would be insoluble solids, that is B. So you have all this information, and using this information and the equilibrium data that is given to us, we will find out percentage oil leached out, and we will also find number of equilibrium stages. So let us move ahead. Okay, let us start solving the numerical. First step is we will calculate F, we will calculate YF, and we will calculate NF. First, let us calculate F. What is F? F is kg per hour of A plus kg per hour of C in the feed. Feed is 360 kg per hour. It is containing 25% oil in it. 75% weight percentage insoluble solid, that is B. But in leaching, F is defined in this way. F is kg per hour of A plus kg per hour of C. Kg per hour of A in the feed is 0. There is no solvent in the feed. So kg per hour of A is 0. Kg per hour of C is weight fraction of C in the feed into kg per hour of feed. Both are known to us. Kg per hour of C is equal to kg per hour of C is equal to weight percent of C in the feed is 25. So it would be 25 divided by 100 into feed rate is 360. So 25 divided by 100 into 360, that is kg per hour of C comes out to be 90. So this is 90. So now F will be kg per hour of A, it is 0, plus kg per hour of C, it is 90. That is F is equal to 90 kg per hour. Even though the feed is entering at a rate of 360 kg per hour, but for our calculation we need F, and F in this case is 90 kg per hour. And how we get 90 kg per hour, it is clear to you. Next, let us calculate YF, calculation of YF. How is YF defined? YF is defined as kg per hour of C divided by kg per hour of A plus kg per hour of C in the feed. That is kg per hour of C in the feed is 90. We have just found out kg per hour of C is 90. So 90. Kg per hour of A in the feed is 0. Kg per hour of C in the feed is 90. So YF is 90 divided by 0 plus 90. That is YF is equal to 1. Then we have to find out NF. How is NF defined? NF is defined as kg per hour of B divided by kg per hour of A plus kg per hour of C. Now in this case, kg per hour of B is weight fraction of B into kg per hour of feed. Weight fraction of B is known to us. Therefore, kg per hour of B is weight percentage of B in the feed is 75. So kg per hour of B is equal to 75 divided by 100 into 360, 75% of B. So that is kg per hour of B is equal to 270 in the feed. So therefore NF will be 270, that is kg per hour of B divided by kg per hour of A is 0 plus kg per hour of C is 90. So NF comes out to be 270 by 90 and NF comes out to be 3. And then we will also find out SN plus 1. That is the solvent, the rate at which solvent is entering into the operation. It is given to us. It is 250 kg per hour. But SN plus 1, the notation that we have used in our discussion, SN plus 1 represents kg per hour of A plus kg per hour of C in the solvent. And in this case, solvent just contains two components, A and C. It is containing 2% of C in it and 98% of A in it. We have just understood. So the solvent that is used, it is containing 2% oil because it is a recovered solvent. That is, it is containing 2% of C, and the remaining 98% is the solvent itself, that is A. So A plus C is 100%, and the feed rate is given to us. It is 250 kg per hour. It is given. So this is kg per hour of C plus kg per hour of A. That means in this case, SN plus 1 is same as that of the rate at which solvent is entering, because solvent is not containing any B in it. Are you understanding it? So there is no need of doing any calculations like we did for F. It is simply 250 kg per hour. Why? Because 2% of this is C and 98% of this is A, and A plus C is SN plus 1 as per the notations that we use in our discussion. So SN plus 1, this is directly given to us, or you can use as it is. It is 250 kg per hour. There is 2% of C plus 98% of A. That is A plus C in the solvent phase is Sn plus 1. Solvent that enters the operation. I hope this is clear to you. If you have any doubts, you please let me know in the comment section. Okay, then next is the very important task, because you will be learning many things in this step. What is the step? Calculation of Yn. And for that, what is Yn? We should first know that. It is kg of C in the final exhausted lever. The exhausted lever that comes out of the operation. Kg of C in the final exhausted lever divided by kg of A plus C in the final exhausted lever. That is Yn. And it is not known to us. We need that in our calculation. So we are going to find out Yn in this step. So Yn is kg C in the final exhausted lever per kg A plus C in the final exhausted lever. And we are going to calculate Yn by using the equilibrium data that is provided to us. So apart from using the equilibrium data for plotting the graph, we are also going to use it to find out Yn. So what is given to us in the equilibrium data? We have various values of kg oil per kg solution in the exhausted lever. So this is kg C plus kg C divided by kg of A plus C. This is nothing but kg C per kg of A plus C in the exhausted lever, and that is nothing but Y. The way we have defined it, it is directly given to us. It is kg C per kg A plus C. So this quantity that is given to us in the equilibrium data, it is nothing but Y. Now let us look at the other quantity. Other quantity, for that we have different values. The quantity is kg solution for kg exhausted lever. This is given to us, but it is not this does not give any quantity that can be, or we cannot use the values as it is, because kg solution per kg exhausted lever, when I say exhausted lever, it contains insoluble solid plus whatever oil is left in the exhausted lever. So you cannot use these values as it is. We need to process those values. And how to process it, I'll tell you. So first what I will do, I have told this. The exhausted lever contains insoluble solids, that is B, and unrecovered oil in it. So it is the quantity in the denominator. Now what I do, I will take reciprocal of this quantity. That means whatever values I have for this quantity, I will take reciprocal of this values. So that means I will be getting kg exhausted lever per kg solution. If I take the reciprocal, this quantity will be converted to this form, kg exhausted lever per kg solution. Now, if I multiply this with weight fraction of B, if I multiply kg exhausted lever with weight fraction of B, what do I get? I get kg of B in the exhausted lever. Kg of B in the exhausted lever. Because now I am using weight fraction of B. So whatever B is there in the exhausted lever, you will be getting it over here. So weight fraction of B into kg exhausted lever is kg of B per kg of solution. So in this case, we get kg of B per kg of A plus C. A plus C is nothing but the solution. In this case, solution is A plus C, solution of oil in ether. So if we take reciprocal of this given quantity and then if we multiply it with weight fraction of B, we get kg of B per kg of solution, kg of B per kg of A plus C in the exhausted lever, and that is nothing but capital N, which we need in our calculations. We need this N. And over here in this 2 or 3 steps, you have learned how you can convert the given quantity, which is kg per solution per kg exhausted lever, to capital N, which is kgb per kg of solution, kgb per kg of A plus C. So first, take the reciprocal of this quantity and then multiply this quantity with weight fraction of B, you are going to get N. So at the end of this particular discussion, you have understood how you can convert the given quantity into N. I hope this is clear to you. If you have any doubts, you please mention them in the comment section. Okay, continuing with calculations for Yn. Yn is, we have defined it. Yn is actually kg of C in the final exhausted lever per kg of A plus C in the final exhausted lever. I have already told you. Then that is Y is kg of C per kg of A plus C in the exhausted lever. And Y is kg of C per kg of A plus C or kg oil per kg solution in the exhausted lever. It is directly given to us. And the other quantity, we are converting it to N. I told you how to convert it into N. So you'll be getting various values of N in that way. Now y upon N, if I take ratio of Y and N, Y upon N, it would be kg of C per kg of A plus C divided by kg of B per kg of A plus C. Since Yn, the task is to find out Yn by using what is known to us. So what I am doing, I am taking ratio of Y and N. So if I do that, it will be kgC per kg A plus C divided by kgB per kg A plus C. So kg A plus C, kg A plus C, it is going to get cancelled out and you are left with Y upon N is equal to kgC upon kgB in the exhausted lever. So kg of C will be easily known to us, kg of B will be easily known to us, and using those two values we can find Y by N. So instead of getting Yn, first we are getting this ratio Y upon N, because for calculating the ratio, whatever is required, it is known to us, or we can make it known, kg of C and kg of B in the exhausted lever. So for the final exhausted lever, that is the exhausted lever that is coming out of the operation, Y upon N, it will be Yn upon Nn. This ratio is for the final exhausted lever. So it is kg of C in the final exhausted lever. Let me denote it as C in FEL, final exhausted lever, divided by kg of B in the final exhausted lever, that is B in FEL, final exhausted lever. Now the equilibrium data, the given equilibrium data is kg of oil per kg of solution in exhausted lever. This is Y. Kg of solution per kg of exhausted lever, this is given to us, but we are converting it to N, and I have told you how to convert it to N. So how are we using the equilibrium data? Y is directly given to us and we are getting N, or we are converting this quantity into N. So let us move ahead. So from this we will find Y by N. So for each of these values, for each of the pair, you can get Y upon N. So let us move ahead. So kgC in the final exhausted lever, the final exhausted lever, it contains 2% of oil on solvent-free basis. That is 2 by 100. 2% is 2 by 100. If we convert it to fraction, it is kg of C per kg of C plus kg of B in the final exhausted lever. But kg of B, which we calculated it earlier, it is 270. It is not going to change. So that means only unknown quantity in this is kgC. So you can easily find out. So 0.02 is equal to CFL, that is kg of C in the final exhausted lever divided by kg of C in the final exhausted lever, CFEL plus 270. That is 0.02 into CFEL plus 270 is equal to CFEL. That is 0.02 into CFEL plus 0.02 into 270, that is equal to CFEL. That is 0.02 CFEL plus 5.4 is equal to CFEL. Please note C of L is kg of C in the final exhausted lever. Since I would be requiring a bigger space to write the entire sentence, I am using this abbreviation. C in final exhausted lever. So if you solve it, it will be 5.4 is equal to C of EL minus 0.02 C of EL. That is 5.4 is equal to 0.98 C of EL. That is 5.4 divided by 0.98 is equal to C of EL. That is C of EL is equal to 5.51 kg per hour. So in this way, we get kg of C, kg per hour of C in the final exhausted lever. And for that, what information we have used? We have used this information. The exhausted lever is containing 2% oil in it. And we have used this information to get kg of C in the final exhausted lever. It is 5.51 kg per hour. So I hope this is clear to you. If you have any doubts, you please let me know. Then we have to calculate yn upon nn, ratio of y to n in the final exhausted lever. So yn upon nn would be kgc in the final exhausted lever, that is C of EL, which we calculated, and kgb in the final exhausted lever, that is known to us, because quantity of solid is not going to change, quantity of insoluble solids is not going to change. That is also known to us. So C of EL is 5.51 kg per hour, and B of EL, that is kg of B in final exhausted lever, it is 270 kg per hour. So yn upon nn is 5.51 divided by 270, that is yn upon nn comes out to be 0.02041. So the ratio of y to n for the final exhausted lever, now we have got it. Please remember, we are doing all this to get yn. Yn is not known to us. So we are going, what we can do with the given values, given quantity, we can find out this ratio. And we have now found out the ratio for the final exhausted lever, the exhausted lever that comes out of the operation. And for this ratio, we are going to find out yn. From this ratio, we are going to find out yn. That is the task of this step, calculation of yn. Okay. Now let us learn how to do that. So for that, I will take the given data, the data that is given to us. We have kg oil per kg solution in the exhausted lever. EL stands for exhausted lever. This is nothing but Y. And kg solution per kg exhausted lever, we are going to convert it to m. And I have told you how to convert it. Here also you will come to know. So in order to convert it to n, what we will do, we will first take reciprocal of this quantity, reciprocal of all these quantities. So that is, we will have kg of exhausted lever per kg of solution, and if you multiply it with weight fraction, you will get kg of B per kg of solution, which is nothing but capital N. So that is what I will, WB is the weight fraction of B in the final exhausted lever, and it is given to us. Weight fraction of final exhausted lever is containing 2% oil in it on solvent-free basis. So remaining 98% is B, insoluble solid. That is, weight fraction is 0.998. Remaining 0.02 is oil. I hope this is clear to you. So this value is converted to N. So it is 0.98 weight fraction of B into reciprocal of this quantity, 1 upon 0.288. So this gives us 3.40. So 3.40 in this case is N. So similarly, all other quantities are converted to N. All other quantities are converted to N. And now we are going to find out this ratio for each of the row, because that we will use to find y, n. I'll tell you. First, we need y by n. So if I take ratio of y to n, I will get this values. That means for every value of y by n, there is a corresponding value of y. And that is the approach that I will be using. Because I know y upon n for the final exhausted lever. That is yn upon nn is known to me. I have just calculated it previously. It is 0.02401. So for this ratio, what is the value of y? And that value of y is nothing but yn. So for y upon n equal to 0.038, corresponding y is 0.1. For y upon n of 0.090, corresponding y is 0.2. Now, for yn upon nn of 0.020401, what is y? And that y is nothing but the yn which I need. And that is what we are doing in this. That is what we are finding out in this step. Our ultimate aim is to know the value of yn. So, from this table, for this ratio, what is the value of n? And that n is nothing but yn. Now, if you look at the entries in the last column, entries for y upon n, let us try to locate this value. Our y by n for the final exhausted lever, it is 0.02401. And if you look at the values, it will lie between the first two values. So it is between 0 and 0.38. That means yn, which I need, lies between 0 and 0.1. And we are going to find out that. So for us, for finding yn, these two entries are important. So let us on the next, and next we will take these two values of y and the corresponding values of y by n. You'll understand it. Let us move it. So now I will take kg of oil kg per solution in exhausted lever, that is y, and then y by n. So first value is 0, y is 0, y by n is 0. The third value is, we know, for 0.1 it is 0.038. But for the final exhausted lever, y by n is 0.0204. This is yn upon nn. And my task is to find out corresponding y for this. And that is nothing but yn. So this is how you can find y. Okay, so now let us use interpolation, linear interpolation for finding out. I will tell you two ways. First is linear interpolation, and then I will tell you how to you can use a graph to find the desired value. Okay, so first look at how to get yn by interpolation, linear interpolation. Now, from this table, the difference 0.1 minus 0 is equivalent to 0.038 minus 0. So that means this minus this corresponds to this minus this. Therefore, yn minus 0 will correspond to 0.02041 minus 0. So when we are able to write this relationships, now we can have cross multiplication. So this is yn minus 0 into 0.038 minus 0. That is equal to 0.02041 minus 0 into 0.1 minus 0. So we are taking cross multiplication in order to get yn. So if you simplify it, this will be yn into 0.038, that is equal to 0.02041 into 0.1. That is 0.038 into yn is equal to 0.002041. That is yn is equal to 0.002041 divided by 0.038. That is yn is equal to 0.0537. And that is what I need. So by using linear interpolation, you can get yn in this way. So we are using the known differences. So point 0.1 minus 0 corresponds to 0.038 minus 0. Therefore, and yn minus 0 corresponds to 0.02041 minus 0. So when I write these two relationship, then next I will use cross multiplication to get the value of y. So this is how you can get yn by linear interpolation. The other way is you can plot the graph. So on y-axis you can plot all y by n values. On x-axis you can plot y. So you'll be getting a curve like this. So y by n is known to me. It is 0.0204. So I can look at over here as per the scale, and then I will move to the curve and get the value of yn. Here also graphically also you get the same value for yn. So yn is 0.0537. That is what I needed. So that ends our calculation for this step. So I hope this linear interpolation is clear to you. If you have any doubts, you please let me know. So you can either use this or this. For this, of course, it is assumed that the curve is a straight line. And over here, if you look at this section, it is almost a straight line. Okay, in both the ways, you are going to get the value of y. Now let us move ahead. Then the first question, percentage of oil leach. So it is given by this formula, or it is simply percent oil leach will be oil in feed minus oil in the final exhausted lever divided by oil in feed into 100. So CFL is 5.5 kg oil in the final exhausted lever. It is 5.51 kg per hour. We have found out. C in feed is 90 kg per hour. We know that. So therefore, percentage oil leached is equal to 90 minus 5.51 divided by 90 in 100. That is percentage oil leached is equal to 93.88. And that is the first question. That is the answer to the first question. What percentage of oil is leached? 93.88 percentage of oil is leached. So that is the first answer to the first question. Now let us get the number of equilibrium stages. So for that we have done the calculations for yn, previous calculations. So we have not used any of the calculations for yn. We are not using yn in this particular calculation. We need yn for finding number of equilibrium stages. So let us move ahead. Okay, now let us get the answer to the second question. Number of equilibrium stages. How to find number of equilibrium stages? So for that we need a graph. A graph needs to be plotted. Graph is between nx versus x, ny versus y, plotted on a single graph. Both the curves are plotted on the single graph. I have discussed this in my previous video. The overflow, in this case, the overflow is not containing any solids in it. What is the meaning of that? All nx are 0. What is the meaning of that? The meaning is nx versus x curve, it coincides with the x-axis. So there is no need of plotting nx versus x curve. Then no adsorption of solute, that is oil, on the surface of insoluble solid. What is the significance of this? All x values are equal to corresponding y values. X is equal to y. What is the meaning of this? All tie lines are vertical. So there is no any task of drawing tie lines. Tie lines are simply vertical lines. So we don't have to use XY plot for plotting the tie line. No trial and error is required for plotting tie lines. Here, tie lines are simply vertical. That simplifies our calculations. So we are going to plot a graph nx versus x, ny versus y. But since overflow is not containing any solids, all nx are 0. So nx versus x curve, it will coincide with the x-axis. There is no adsorption of solute on the surface of insoluble solid. That is, x is equal to y, which means all tie lines are vertical. So there is no need of using trial and error to plot the desired tie lines. And this is true for this particular problem. If x is not equal to y, then you will have to plot the tie lines by trial and error. I have discussed that in my previous videos. You please watch those videos, you'll learn. But in this case, tie lines are simply vertical lines, so no any trial and error business in this case. So let us find the number of equilibrium stages. Let us plot the graph. Nx and ny, they are plotted on y-axis. X and y, they are plotted on x-axis. So in this case, nx versus x is going to correspond with the x-axis. So the curve that you will be getting is ny versus y curve. No need of plotting nx versus x curve. It coincides with the x-axis. Why? Because there are no solids in the overflow. So first, you will locate point F. Point F is located at YF NF. YF is 1, NF is 3. So YF, I'm locating over here. NF, I'm locating over here. I get this point. This point is nothing but point F. Then we have to locate point Sn plus 1. It is located at xn plus 1, nn plus 1. We are going to use xn plus 1. Xn plus 1 is 0.02. What is the reason? The reason is entering solvent contains 2% oil in it and 98% ether in it. So Xn plus 1, which is kgc per kg of A plus kg of C, it is 2, which is directly 2%, it is directly given to us. Therefore, Xn plus 1 is equal to 0.02. The entering solvent contains 2% C in it and 98% ether in it. So we are going to use xn plus 1 to locate it. It will be located on the x-axis because n plus 1 is 0. There are no solids in the entering solvent. So Sn plus 1 will be located over here. So after locating Sn plus 1, we are going to connect points F and Sn plus 1 with a straight line. So point F and Sn plus 1, they are connected with a straight line. So you have to follow these steps in order to construct the diagram that can be used to find the number of equilibrium stages. Okay, next we have to locate point M. It will be located at Ym Na, but we don't know. We have to find Ym and Na. So Ym is F into Yf plus Sn plus 1 into Xn plus 1 divided by F plus Sn plus 1. So I have discussed this equation in my previous video. So F is given to us, it is 90 kg per hour, or we have found out F. Sn plus 1, we know that it is 250 kg per hour. Yf is known to us, it is 1, and Xn plus 1 is also known to us, it is 0.02. So Ym will be 90 into 1 plus 250 into 0.02 divided by 90 plus 250. That gives Ym as 0.28. So you can use either Ym or Nm, no problem. But I'll tell you how to calculate both the quantities. Then Nm is given as B upon F plus Sn plus 1. F is 90 kg per hour. We know that Sn plus 1 is 250 kg per hour. B is 270 kg per hour. We have calculated it earlier. So Nm will be 270 plus divided by 90 plus 250, which gives us Nm as 0.79. So now we have got Ym, we have got Nm. Let us move ahead. So now let us locate point F. It is located at Ym Nm. I told you. Ym we got 0.28. Nm we got 0.79. So let us use 0.79. 0.79 is over here on the y-axis. You go to the line Fsn plus 1. The intersection point is nothing but point M. And if you check the value of Ym, you'll find that it is 0.28. So our location of point M is correct. Then we have to locate point UN, and over here we need YN. The calculations that we did for finding out YN, we need it over here. It is located at YN. Only YN is required. No need of using YN. So YN is 0.0537. We have found out it earlier in our previous discussion. So you just have to locate 0.0537 over here. Go to the upper curve. The intersection point is nothing but UN. So after locating UN, you draw a line from UN through M and extend it so that it intersects the x-axis. The intersection will give us O1. So I start at YN, pass through M. I start at UN, pass through M and get this point. And I am calling this point as O1. So this is in this way you have to draw all those lines. You have to locate all those points. I hope you have understood it. If you have any doubts, you please let me know in the comment section. Now let us move ahead. So now, once you have this, the last important task that we need to do is, we will draw line FO1 and extend it. We will draw line UN SN plus 1 and extend it. And we will get intersection of these two lines, and the intersection point is delta R. So I draw FO1, extend it. Then I draw UN SN plus 1, extend it. I get this. This point is delta R. So after locating delta R, now we can start our task of finding number of equilibrium stages. We will start at O1. Here at O1, the x coordinate is x1. Now since we have to draw a tie line, but here tie line will be vertical tie lines. So there is no need of using tri-linear. So simply draw a vertical line through O1 and you'll get the intersection on the upper curve. So that will be Y1. Now once you get this point, next you connect this point with delta R, because here you have obtained underflow from first stage, and now you are contacting with the solvent that is coming from the other stage. So that you can show it by connecting with delta R. So in this process you get this point. This is nothing but x2. And now draw a vertical tie line from this point to get this point. This point is white. So this brown color lines, these are tie lines. Then connect this point to delta R. So in that process you get this point. This is x3. Now draw a tie line through x3, vertical tie line, simply vertical tie line, you get this point. So this will be y3. And then connect this point with delta R. So you have connect this point, you get this, and in this process you get x4. And if you draw a tie line from x4, point UN is crossed. So once point UN is crossed, you have to stop. And once you stop, you count the number of tie lines that you have drawn in the process. So this is number 1, this is number 2, this is number 3, and this is number 4. And what is your conclusion? Since we have drawn 4 tie lines in the process of reaching YN, the number of stages is equal to the number of tie lines you draw. So in this case, the number of tie lines are 4. Therefore, the number of equilibrium stages are 4. Now, in this particular numerical, the task of drawing tie line was an easy task. We just have to draw vertical tie lines. This is possible when there is no adsorption. where x values will be equal to y values. So with this, I end my discussion. So in this way, we get number of equilibrium stages is equal to 4. That is the answer to the second question. Number of equilibrium stages is 4. So I hope you have understood how to find out the equilibrium stages. If you have any doubts, you please mention that in the comment section. With this, I will end my discussion for this numerical. I have told you how to find out percentage leaching, then how to find out number of equilibrium stages in a multi-stage counter current leaching operation. So let us end the discussion for this numerical. I hope you have learned. If you have any doubts, you please mention them in the comment section. So thanks for watching this video. I hope you must have learned how to find the number of equilibrium stages. Do subscribe to my channel, tell your friends to subscribe to it, and hit the bell icon so that you will be notified as soon as I upload any new video on my YouTube channel. For now, have a nice day. Take care. Bye bye.